So we're going to continue looking at horizontal circles. One really neat application of horizontal circles, Zach, would be generating artificial gravity for outer space. So one method of generating artificial gravity in outer space would be to build a circular space station and spin it. So here's a side view of the spaceship, and it would be spinning. Here's a top view, spinning in that direction. Okay, so if this space station has a radius of 35 meters, what does the period of rotation need to be for the astronauts to experience 80% of Earth's gravitational field? So 80% of gravity. Not full gravity, but enough that you'd feel fairly normal. You'd feel a little bit weird, a little bit lighter, but pretty close. Any suggestions on how I might want to start? I think I'd start with a free body diagram. Which one? I think I'm going to use the top view. Okay? What are the forces acting on this person? Ooh, wait a minute. Are we in outer space? Okay, no gravity. I was going to stick mg on there. No. What else? Well, what path is this person tracing out? So where must there be an unbalanced force pointing? Got to be a force pointing towards the center. I know there has to be a force there. What force is that? Well, maybe it's gonna be Fc, but that doesn't show up on my free body diagram. That's the right-hand side of my winner minus loser equation. What force is that? And I guess in this picture it would be right there. It's a normal force. It's the ground pushing up through this person's feet. Yeah. It's a normal force. In fact, as an equation, what we have is the normal force is what's pushing us in a circle. Fn equals mac. On the right-hand side, it's going to be m, and then which version of A am I going to use? And how do I know? Because they're asking for the period. So I'm going to use the 4 pi squared r over the period. Squared. Thank you. Wow. That would have been bad. 4 pi squared r over the period squared. What about the left-hand side? I don't know the normal force. And I can't really say, oh, but look. I know another size, a force the same size as a normal force. Or, can I? How big is the normal force? Loud and proud. 80% of Earth's gravity. 0.8 mg. Oh, could little kids and grown-ups live on this space station? Would they all experience 80% of Earth's gravity? Why? Oh, that's convenient. Oh, I like this question. I like this question not just because I like this question. I like this question. I like this, but outer space travel. As far as I'm concerned, there are 3 variables: how strong you want gravity to be, the radius, or the period. Or I could have asked for it in terms of how fast does the spaceship need to spin. There's a V. I can give you any 2, find the third. Here they want me to get the t squared by itself, or the t by itself. Where is the t right now? On the... Yeah. But stuff can move diagonally. This is 1 fraction equals 1 fraction. It's actually 0.8 g over 1. So I can rewrite this as t squared equals 4 pi squared r over 0.8 g. Now what? So the period is going to be the square root of 4 pi squared 35, yep, all over 0.8 times 9.8. I get 13.3 seconds. The space station needs to rotate every 13.3 seconds. What if the period got larger? What would happen to gravity? What if it took longer to go around? Well, if this is fake gravity, as the period gets bigger, what happens to this answer? In other words, if we didn't have a 0.8 g there, really what we're saying is this. Fake gravity, that equals m4 pi squared r over t squared. So as this gets bigger, if it's taking longer to go around, what happens to this as an answer? Y'all got excited? The power's not going to go out? Smaller. Okay, so the more time it takes to go around, the weaker gravity is. The less time it takes to go around, the stronger gravity is. Okay. That's kind of cool. What about if the radius got smaller? What if there was a ladder leading to the center of the spaceship? As you climbed the ladder, well, that's a good follow-up question. Part B. Suppose the astronaut begins to climb a ladder that leads to the center of the space station. At what radius will the astronaut feel 30% of his weight or her weight? I think we're still going to say the normal force is what's pushing us in a circle. But how big do we want the normal force to be this time? 30% of mg. That's going to equal m4 pi squared r over t squared. Little kids and grown-ups would both feel 30% of their weight. Remember, weight is mg. It's not m. It's mg. It's measured in newtons. What do they want me to get by itself this time? R? I guess divide the 4 pi squared. Stuff moves diagonally. Multiply the t squared. I think we'll get this. R equals 0.3 g times t squared all over 4 pi squared. It's going to be 0.3 times 9.8 times 13.3 squared. I'm going to use my answer button there. Divided by 4 pi squared. 0.3 times 9.8 times answer button squared divided by bracket 4 pi squared. Again, I encourage all of you to type this in. There's a chance that some of you might get an error depending on how you type it in. I get 13.1. meters. What will the fake gravity be at the very, very center of the space station? 0. Yeah. So if we ever do build large generational ships, and if we do use artificial gravity, spinning to create artificial gravity, first of all, at the very center there would be a 0g section, and then just off of that there would be a section where g was maybe 0.1 or 0.2 meters per second squared. You could do some really, really interesting activities there. For example, in that gravitational field, you might be able to strap wings onto your arms, and you could actually fly there just by flapping your wings like a bird. You could have all sorts of recreational sports and activities there. What would a swimming pool look like there in a situation like that? That would be kind of interesting. There's all sorts of neat kind of ideas. But it's also a bit of a problem. You've all turned the page. That's okay. What was the original radius of this space station? How many meters? 35. That's not that big a radius, especially when compared to your height. Your height is actually a fraction of that, not an insignificant fraction of that. And what that really means is when you're standing up, the fake gravitational field on your head would be different from on your feet. And it would probably feel a little bit odd. If you were facing the direction that the space station was rotating, it would probably feel like you were about to fall backwards until you just slowly got used to it. Something would just feel off, feel a little weird. For what it's worth. But certainly this is one way that we've considered to build spaceships with fake gravity. It's the easiest way. Put your pencils down, look up. There's some other issues with doing this that are not immediately obvious.
Last video, I was at the Ashton Graybiel Spatial Orientation Lab at Brandeis University, and while I was there, one of the team just casually mentioned that they have an artificial gravity laboratory.
Artificial gravity facility sounds like something out of science fiction, but it's not, and there's very much a reason why I'm keeping my head straight and forward at the moment. This is the artificial gravity facility, otherwise known as the rotating room. So, let's do some experiments. This is unscripted. I don't know what's going to happen now. Other things are going very weird when I move my arm.
Okay, so it's a room that rotates. No one has invented science fiction gravity generators yet. But if you have a theoretical spaceship going to Mars and you wanted to generate apparent gravity to keep astronauts healthy, that's what you do. You would spin up the ship and use centrifugal force. And that lab is the research prototype. How do humans deal with a very strange gravitational environment?
The first thing that you should do is try to push yourself off the wall and align your body with the direction of the resultant.
Oh, okay.
So that feels like he's standing up vertically right now. Now this is because, unlike in outer space, there is gravity here. So it's a combination of gravity down and the normal force pushing him around. When you add them tip to tail, you're getting roughly a 45-degree angle. Weird.
Now you're standing upright.
Wow. Can I walk, or is that gonna...
No, don't walk. It's a little dangerous.
It is almost impossible to envision long-duration space flight without artificial gravity. The best way to study artificial gravity on Earth is to build a rotating environment. We started designing it in the mid-'80s. Ideally, we want to study its effects on the human body, and we want to learn also how to pre-adapt astronauts to the force of artificial gravity. In 99.9%, those will be highly dysfunctional individuals until adapted.
They have NASA standard sick bags for everyone, by the way. I was required to keep one in my back pocket throughout, just in case. Because if you tilt your head too fast, your inner ear has no idea what's going on, and things go wrong very quickly.
So now you're going to see some of the strange issues that aren't immediately obvious if we do have an artificial gravity by having a spinning room.
You now move your arm and try to go as straight as you can.
Oh!
So he thought he was doing this, and you can see his arms moved way off to the left. So if you're an astronaut and you're trying to do a very important fine motor control, or you're controlling jets for the landing, that's bad. If you tell your brain tells your arms to do something, and they don't behave the way you're expecting.
Oh, I moved my head.
You shouldn't move your head.
Do you get used to this?
Yeah, you get used to it, yeah. You can adapt. Move your arms and try to feel this force that is...
Oh,
that is...
Okay, just to be clear, I'm not putting this on. As far as I'm concerned, the signals I'm giving to my muscles, I'll move my arms forward. And now I'm forcing them. But I'm pushing against a force here.
If you keep going, at some point...
By the way, there is no force. What he's pushing against is his arm's inertia. But because he can't tell that he's spinning, because the room that he's in is spinning with him, his eyes are telling him, you're not spinning. Something weird's going on here. This is where you also might start upchucking, right?
You won't feel the force anymore.
Oh, that's weird.
That's weird, right?
That's so...
So now, after doing that a few times, suddenly his brain has adapted. He can no longer feel that force pushing him. Now the astronaut's brain has adapted. Now, when he moves forward, his arm will move straight forward. But there's that adaptation moment there.
So weird.
So now we are adapted.
So if I try to do anything else, I haven't adjusted to it. But that specific movement, my body's got used to.
That's right.
Wow.
One way to visualize this force is for me to try and throw a little tennis ball at you. I will throw it straight at you and see what happens, okay?
Whoa! What? I'm struggling to work this out because in my head, this is a normal reference frame. But it's clear.
And now I'm going to throw it over there,
yeah.
And hopefully it's going to get at you.
Okay.
Are you ready?
Yeah, ready. Yes!
Oh, nice. Great.
So even the physics of passing something to somebody else in a situation like very different, there would be some serious adjusting having to go on here.
Wow!
All those odd effects are from the Coriolis Force. It's not a real force acting on the ball, but it looks like one when you're in that weird rotating environment. Have a look at this 360-degree image of the lab. Now, it's a little distorted because it's from a single camera in the middle, but it's close enough. Here's the tricky part. The circumference of a circle is longer the further out you go from the middle. But because everything in that circle is rotating at the same speed once around every 6 seconds, things on the outside have farther to travel. So they're moving at a faster speed than things on the inside. On the outside, we're moving pretty fast, but that camera in the middle is just spinning on the spot. So let's mark the sideways speed that everything is moving at relative to the rest of the world. Green is fast, red is slow. When you throw a ball across that room, it keeps that sideways speed that it had when it left your hand as it travels into slower moving areas of the room. Now, out at the edge, that was fine. It was going the same speed as everything around it, so it looked like it aimed for the center. But by the time it starts to get there, it's a missile flying outwards compared to everything around it. Now, from the outside, that makes sense. After it leaves your hand, the ball just moves in a straight line. From the inside, it looks like there's a force suddenly sending it sideways, and that is the Coriolis Force. And it's not something your brain has evolved to deal with.
Now, if you move your arms, you're pretty much fine. Just by moving around.
So his brain is adapted, but only that specific movement. If he tried walking, he'd almost certainly wipe out. He'd have to adapt to that. So every movement would need to get adapted to. That's going to take a while.
You've been adapting.
That's ridiculous. Thank you so much. I'm going to throw this at you one more time.
The question that lab needs to answer is, can humans adapt to that over time? And if so, how long does it take them to come back down to Earth?
Let's bring this to a stop.
Great. Abby, can you bring us to 0? Bring your hands down and don't move.
Okay, so now they've stopped, and there's still problems.
I swear, the room is...
Oh, that's weird. I think we're stopped. So try to swing your arms in front of you.
Now they're compensating in the other direction, and his brain is adapted, but now his brain doesn't realize he stopped. Now they're going in the opposite direction. These would be issues in a Mars mission. Okay, we stop spinning the ship, you get into the spacecraft, because now you're going to land a little lander on Mars. But when you reach for a control, you miss the control, and that's not good. So there's all sorts of subtle issues with fake gravity that we'd have to deal with.
I don't like that.
You've been adapted. There are no unusual forces on your arms, but you feel it, right?
Yeah, but still doing that.
And now you have to readapt.
Thank you so much.
Thank you so much to everyone at the Ashton Gradle Spatial Orientation Lab at Brandeis University. Pull down.
So, some issues with artificial gravity. I think the movies should also include that. That would make it a good sci-fi movie, also more interesting, I think. Another great example of a horizontal circle is the Gravitron. This is the ride where often you're laying against the wall, and there's two versions. So the ride starts to spin. In one version, the floor drops away. In another version, the ride tilts vertical. How many of you have been on the Gravitron before? Okay. To my shame, until only about 4 years ago, I had never been on it because the P&E owned the Gravitron. I always went to Playland every year with my physics students, and I wasn't going to pay extra money to go again to the P&E. But a few years ago, when the roller coaster was broken for Playland Physics Day, they brought out the Gravitron, and I finally went on it. I would love to go on the Gravitron and do a bunch of experiments similar to that rotating room. I would love to try playing catch, for example, or have a Nerf dart gun and try shooting the Nerf dart gun, because you would, again, see that strange Coriolis effect. It would be really, really cool, I think. Anyways. Oh, I like this question. There's going to be a Gravitron on your test. It says, Gravitron spins its riders around in a circle. This is the version where the floor just drops away. We're not going to add suddenly tilting vertically. That would be a vertical circle. We're looking at horizontal circles. If the ride has a radius of 4.8 meters and it rotates every 2.5 seconds, A, what is the minimum coefficient of friction required between the riders and the wall of the ride? What's this question asking me to find? What's mu? I don't know what's mu with you. It's asking me to find the coefficient of friction. Any suggestions on how I might want to start this? Free body diagram. You know what? They gave me a picture, so I'm going to label the picture. Here's the person. What are the forces acting on this person? Can we get the obvious one? Are we back on Earth? Yeah, which way? Okay. Is this person sliding down the wall? Is this person sliding up the wall? So vertically, it seems to me the forces must be, I'm looking for a word that starts with the letter B. There has to be an arrow pointing up the same size as gravity. I'm, gotta be honest, not quite sure what that one is yet, but I know it's there. I'll come back to it. I'll figure out what it is in just a second. What else? What path are we tracing out? A circle. Where must there be an unbalanced force pointing? Toward the... So I know there has to be a force in this direction. What did you suggest it was? Does that give you a hint as to what that pointy uppy force might be? Ah! Not used to friction being vertical. Oh, wait a minute. If it's a vertical wall, then friction would be vertical in the same way when it's a horizontal floor, friction is horizontal. Okay, I'm okay with that. So what's my equation? Okay, friction equals MAC? You're telling me that's what's pushing me in a circle? No, it's not. What's pushing me in a circle? Ah, my equation is this. Normal force is what's pushing me in a circle. And of course, you have your formula sheet out by now. You want to look at which version of AC am I going to use? Well, I'm going to read the question. Oh, they gave me the period. They could also have given me the speed, but they gave me the period. So on my next line, it's going to be M4 pi squared R over T squared. On the left-hand side, I don't know the normal force. And I can't say, oh, but look, there's another force the same size. That would be a force pointing out this way, and there isn't one. I don't know the normal force. What do I know? There's a second equation that I can write from this free body diagram. Everybody see it? Guy, you're nodding? Which one? No. That's not out of this free body diagram. Write a vertical force equation. Are we sliding down? Are we sliding up? I can also say, and I'm going to do this over here, friction equals mg. That has to be true. Friction is what times what? So, mu times the normal force equals mg. Oh, let's get the normal force by itself. What's the normal force here? How would I get the normal force by itself here? So, I'm going to argue that in this situation, the normal force is equal to mg over mu. Jarman, what's the normal force equal to? What can I replace the normal force with? Same answer. What can I put right there in place of the normal force? Oh, can little kids and grown-ups go on this ride? Well, that's kind of nice. If you look, we now have, as far as I'm concerned, 4 variables. R, T, mu, and I could put you on a different planet, different G. As far as I'm concerned, if I can give you any 3 of these, you can find the 4th now. Okay? What are we trying to find? Where is it right now? Yeah, it's on the bottom. Oh, wait. Stuff can move diagonally. So I think I'll get this. GT squared all over 4 pi squared r. I think that equals the minimum coefficient of friction. Is that right? So it's going to be 9.8 times 2.5, don't forget the squared, Mr. Dewick, all over 4 pi squared times 4.8. And I get 0.323. Now, that would be the minimum. If that's what you had, you would feel like you were just about to slide up or down. You would not, you'd feel kind of like you were laying on ice almost, like, ah! So you'd build in way more than this. But minimum, okay. What's B you want me to find? Centripetal speed. We have an equation for that on our formula sheet, don't we? I think VC is 2 pi r over the period. Do we know r? Do we know the period? Oh, plug and chug. 2 pi 4.8 all over 2.5. I get a centripetal speed of 12.1 meters per second. Part C says, what's the frequency? I'm skipping that this semester. For what it's worth, frequency is the reciprocal of the period. So the frequency would be 1 divided by 2.5. This ride has a frequency of 0.4 hertz. So period and frequencies are reciprocals of each other. Frequency is measured in hertz, which is cycles per second. Period is measured in seconds per cycle, or just seconds. A little nerd trivia for you there. It says, show Gravitron picture. I think I got it here, Mr. Dewick. Gravitron ride. I think this is it. Okay. Well, but I think he's feeling a very different fake gravity on his head than on his feet. You would have to practice this. I think you'd be going through some similar feelings that Tom Scott went through in the video that I just showed you in the rotating room, but maybe even more magnified because there's a bigger difference between your head and your feet when you're pointing your body in the same direction as the centripetal force. So, Gravitron. I like that question. I like that question. I like that question. Example 3. The picture below shows a frictionless tabletop in top view. The mass is 4.15 kilograms. It's attached to a 2-meter long string. It's moving at 2.5 meters per second. Write force equations and solve for the string tension. Okay. This is a top view. I guess since it's wanting me to find tension, this is a job for a free body diagram. What are the forces acting on it? Get the obvious one. Which way? Into the page. I'm going to remember that it's there, but I'm not going to try and draw into the page. Because is it sinking into the table like quicksand? Is it flying out like Superman? Then I think normal force would be coming out. And there's no friction. It does say frictionless. What path are we tracing out? So where must there be a force pointing? Toward the... What force is that? Ah! You know what my equation is? I think my equation is tension is what's pushing me in a circle, or pulling me in a circle. Tension equals M. Which version of A am I going to use here? Oh, they gave me a V? Does the M cancel here? No. Well, which makes sense. Put a bigger mass on. That's going to take way more force to spin it across, to spin it around. It's going to be 4.15 times 2.5 divided by 2. What do you get? 13? So 13.0, is that right? And newtons? Again, for those of you who have been on a child playground merry-go-round, if you ever get a chance to go on one again, things for you to notice. As you walk towards the center, what happens to your centripetal speed? Increases, decreases, or stays the same? Decreases, and you can feel that by just the wind on your face. That's a good speed indicator. It doesn't let you figure out the magnitude, but it lets you figure out at least the intensity. You'll find at the center, not much breeze at all. We're on the very, very edge. Big breeze on your face. If you're walking on the merry-go-round with your hands in the air, so you're not holding on to the railings, which force is pushing you in a circle? So replace this free body diagram picture, remove the string, make it a person. What force would be pushing you in a circle? Ooh, this is stumping you. I should turn this into a thought puzzle. Air resistance? No. What? Friction. If the merry-go-round is made of ice, you're sliding right off. You can't stay in place. Okay? Or you need to grab the railings. Now, normally you're grabbing the railings. It's the combination of the friction between your feet and the merry-go-round and your arm. But if you try just holding up, you'll find you probably have to lean forward a little bit like Tom Scott did in the video. You have to do that actually to increase the friction. You're actually trying to get a better normal force vector angle. It's kind of complicated. But again, if you got a chance to play on a playground merry-go-round, push the kids off nicely, do so. Example 4 is kind of cool. Was there a part B? I think that was it, right? Yeah. A 9 times 10 to the negative 3 kilogram ball is attached to a 3.6 times 10 to the negative 2 mass, big M. Okay, bigger mass hanging down, smaller mass hanging up by a string which passes through a hole in a frictionless surface. The ball travels in a circular path of radius 0.42 meters. What's the speed of the ball? I guess we've got kind of an equilibrium situation there. Now, how is that possible? Sorry for those of you at home on YouTube, this isn't going to translate well, but here's Mr. Dewick's version. I'm going to hang a mass on this little ball down here. And obviously, if I just let this go, it's going to pull this top ball right down. However, if I spin it, right, I can find an equilibrium point. That's what's happening in this table. The reason they put the table there is if you were to zoom in, this circle is at a slight angle. The ball is moving at a slight angle. It's not a dead horizontal circle, and that makes the physics tougher. So imagine I was doing what you can see, but doing this on a table. What's going to happen if I slow down? Will this mass move up or down if I slow down? What if I speed up? Okay. You can really control it pretty good. Okay. So there's kind of a visualization of what's happening here with the table. And again, the table is there so that we know that that circle is dead horizontal, not at an angle. What do they want me to find? I think this is a job for a free body diagram. So let's draw a free body diagram on the little m, on the ball. What are the forces acting on it? Get the obvious one. Okay, so I'm going to have little mg, and I guess normal force pointing up. What else? In fact, I think this is the equation here. Tension is what's pulling little m in a circle. Which version of A am I going to use? Oh, they asked for the speed? Okay. So it's going to be little m v squared over r equals tension. Do I know little m? Check. Do I know r? Check. Do I know the tension? Ooh. I do? 9.8 times, you're telling me tension is mg? I don't think it is. What haven't we used yet? How about we do a free body diagram on this guy? What are the forces acting on this guy? Get the obvious one. I'll call that big mg. What else? Ooh. Is that tension the same as this tension? Is it the same rope? Then it is. Let's write an equation for this. For this here, who's winning? No one. So what does that mean? It's balance. It's a tie. You know what? I think I can say tension is equal to big mg. Zach, what is tension equal to? Big mg. What is tension equal to? So what can I replace tension with? Same thing. So over here, big mg equals little m v squared over r. So you were right, sort of. It is a force of gravity, not the one you were thinking of. It's the other one. Because this is in balance and equilibrium. Now I can get the v by itself times the r, divide little m, square root. And I get, my friend, the square root of GR again. Kind of hidden, but there it is. So I've probably done this right. V is going to be big M, 3.6 times 10 to the negative 2. 9.8. What was R? 0.42. All over 9 times 10 to the negative 3. seems, oh, square root. Did I make a typo at all? Looks good. You get 4.06 meters per second. So this is going to sound weird, but Tara, hopefully you didn't technically learn anything new today. This was just more applications of horizontal circles. I'd give you some trivia about artificial gravity, but I'm hoping you would have figured that out. What's your homework? So you can try, I know I got some videos to show too, but you can try number 1. 2 is good. 3 is good. 4 is good. 5 is good. You can skip 6, 7, 8, 9, 10, and 11. 12 is good. 13 is good. So I assigned all of them. Those of you that know me well know that I like juggling. I have a bit of an obsession over it. So this was something I came across. This is juggling in a cone. Pardon me? Look like money. There's some cool videos though. If you're bored, try following one of the balls with your eyes and you can see the pattern that it traces out. Some interesting physics going on there. If any of you are good at welding and making things, this is something I think you could make some good money from. In the same way that people build what's it called? The fake bucking Broncos. They'll have those, and you can try and ride those and see how long you can stay on those. I think you could make some money taking this to like parties and fairs. This is something called Centrifury. It's a really neat idea, and I'm surprised no one has tried to market this.
No, I can hold longer than you.
Right, anyway.
So they called it Centrifury.
Alright, object of the game. Don't let go.
So it's a two-person competition. You have to hold your hand on that winner button. Whoever lets go last wins. But it's going to spin you faster and faster and faster, so you'll have to use more and more force to maintain your position.
Here it comes.
I think you could probably charge $10 per rider for the competition, just for bragging rights. People would do that to try and compete against their friends. If you mounted a camera for each rider, you could even sell them the video of their competition, because they're going to be making some strange faces. So I think that would be a good game. If you're looking for something, a marketing idea, you're good at welding, you'd have to make sure it was safe and all, but I think it'd be pretty cool. And then the last one is called the India Circular Wall of Death. These are very, very common at India state fairs or carnivals. But I remember actually seeing this live back at the P&E when I was about 9 years old. What are the forces acting on him? Get the obvious one. What else? I think friction pointing up. You know what? It's the same free body diagram as the Gravitron. Normal force is what's pushing him in a circle. Gravity's pulling him down. Friction is pointing up as long as he's got good tires and he goes fast. Oh, and if he goes faster and faster, since friction is mu times the normal force, he can increase the normal force and therefore increase the force of friction, making sure that gravity won't win. Physics and cancels. So I clearly remember I'm maybe 8 years old, 9 years old, and they had this set up at the P&E. And to tell you how long ago this was, what the person in the window did, they would just hold their hand up and people would hold out dollar bills. This was long enough ago that there was still a dollar bill, and he would just grab the dollar bills, and that was his tip. So you got the remainder of class. You can work on the homework and also work on the stuff from last day. We're basically done the unit. I'm going to be doing a lesson tomorrow. You're going to get a take-home quiz tomorrow. You're going to get another take-home quiz on Thursday. I'm thinking we can do our unit test on this a week from today, on Monday. Okay? Or sorry, not a week from today, 6 days from today, because today is Tuesday.